So I'll start off with just a few class announcements. So, well, this is probably intended for the people who aren't here right now, but the Canvas page mistakenly said that we were only meeting on Tuesdays. We're actually meeting every weekday. Oh, okay, more people are showing. I guess it's okay. But yeah, I changed that, so it does say that we're meeting every day. But like I said before, I'm not going to be taking attendance, and so the the live meetings aren't in. So if you can't make it, you can watch the recording later. So I haven't put up any of the recordings yet. Sorry, my my voice is a little scratchy today. I haven't put up any of the recordings yet because I need to edit out sort of the beginning where nobody's here and the end where people are talking to me after class. So once I get some editing software to do that, I'll put them. Let's see what else. Nobody has emailed me to let me know what times are good for them for office hours. So I will probably just pick whatever day and time is good for me, unless somebody says otherwise. We have a class schedule. It's only a partial schedule, so I'll show you this. Share my screen. So on the Canvas page, under Files, you can go to Course Schedule, and the only file in this folder is schedule.pdf. Now, for the first 2 weeks, it has listings for readings from the class notes from the jury level book that we're looking at, and then the other book that's on the list of. These are all freely available. So it has listings for all these, but starting from week 3 on, it only has readings from the notes. So I will try to fix this and put it on the front page of the Canvas page, so we can all follow along with it, and I'll put the videos, all that stuff. There are some recommended problems over here. Like I said before, these are recommendations. I'm more than happy to look at whatever solutions you come up with and give you feedback and talk to you about them, everything like that. So I really do encourage you to take a look at those. But yeah, this is just a tentative syllabus, and once oh yeah, like I said, I guess I said this after class, but this is just a sort of a rough sketch of how we're going to follow things. It's quite possible that we could go through the topics a little more slowly, and so we might not cover as much in this schedule. Okay, so I think that's everything I wanted to talk about. Anybody have any questions or comments before we get started on math stuff? All right, so I've got my tablet today. I'll try to set up. So I'm going to continue following the JL book. Let me see if I can. That's so. Just get my windows rearranged. Okay, I can see it. Okay, so I'll start looking at chapter 1 today. Things are probably going to seem a little scattered at the beginning because the resources for the class are still kind of trickling in, but hopefully things will settle down. Also, I'm spending most of my time preparing for my dissertation defense on Monday. After that. Okay, so the first chapter starts off talking about well, I guess the first chapter is about first order ODEs. So what we're talking about first order ODEs. And so the first part of this is the ODE part, the ordinary differential equation. And you'll recall that this means that what we're looking for as a solution is a function of a single variable. So we want a function of a single variable. And so we'll oftentimes write this as y of x to indicate that y is the function of a single variable x, or sometimes x of t when we think of t as being a spatial, or t as being the time dimension and x being a spatial dimension. Again, those are just physical interpretations. Those are interpretations of things in the real world. But in mathematical terms, there's no difference. They're just symbols. Okay, and now first order means if I can remember how to write in the English language. The highest order derivative is first order. So we only have the first derivative of our function y. We'll stick with this convention for x. Okay, so the way this looks is we are saying dy dx is equal to, and then something in terms of y and x. So we'll just write that as f of xy. And this just means all of the stuff that all of the expressions or functions or things in terms of x and y, we just kind of collected them together in this one term that we're just calling f of xy. Alternately, we could write dy dx as y prime, and it really means the same thing. Occasionally, this is called Leibniz notation. And this is named after Wilhelm Gottfried Leibniz, one of the calculus, along with Isaac Newton. And it's occasionally suggestive of things that we can do to manipulate a derivative. So it's sometimes useful as a way of remembering. Okay, so the book starts off with the very simplest possible scenario that we can come up with, and that is when we have, let's actually write it like this. This is the simplest case. So the simplest case is when we have our derivative of y. This is a function of x and y. So what if this derivative is equal to something that's only written in terms of x? So our derivative of y is just a function of x. Now there's nothing in there in terms of y, and so this is sort of like just a regular calculus 1 or calculus 2 problem. What we want for y, so y is whatever we need so that the derivative of y is equal to f of x. And of course, we know what that is. y is the antiderivative of f. So when this function that we're saying y prime is equal to is just something completely in terms of x, then this becomes simply an integral problem. It's taking the integral of the antiderivative. And the JL book goes into a little bit of technicalities about that. We'll kind of gloss over that a little bit. But basically what we're going to do is we'll take this y prime equals f of x, and we'll just simply take the derivative with respect to x on both sides. Since y is a function with respect to x, y prime will also be a function with respect to x. So we just do this. And so we this right here will be equal to y of x, or right here. And this will be some integral that we solve using the good old techniques of integration. So just for the sake of remembering, we whenever we do an antiderivative or an indefinite integral, we always end up with a constant on the other side. Okay, so the interesting point of that kind of technical discussion in the JL text is that we often think of the antiderivative and the indefinite integral as the same thing. But if we're being really precise, we only want to talk about there being one kind of integral, and that's the one that gives us a number at the end. It might be expressed in terms of symbols, but ultimately what we're getting out of it is a number. Remember, the integral is supposed to represent the area under a curve, right? It's supposed to be like a geometry. So the antiderivative doesn't give us that. It gives us a function at the end. And so we do want a function of x, but a way to kind of get around this is to write this as a definite integral. And so what we can do is, instead of writing this, we'll write y of x equals the integral from x0 up to x of f of s ds. Let's see. And we call this s here a dummy variable, or a variable of integration, whatever. And so this is just a variable that we introduce so that we don't use up the x in the expression that we wanted in order to have it at the end. So this definite integral will be a function of x. So for any specific value of x, we get a specific number out of this definite integral. So this kind of satisfies the need to talk about the integral only in terms of the definite. Now there is a nice consequence of this. Well, first let's do an example. So there's an example that comes up in the text, so we'll do that first. Example. We want to find the general solution of y prime equals 3x squared. So now we're in the sorry, excuse me. we're in the same setting that we were just talking about. We have the derivative of the function that we're trying to find being expressed entirely in terms of x. And so what we can do is we can say y of x simply the antiderivative 3x squared plus c. All right. Right. And we know what the antiderivative here is that's just x cubed. So that's just a simple example. We're just doing a plain old integral. Sorry, I didn't mute my phone. Okay. Setting a bad example already on the second day. So let's see. Now, the nice thing about this definite integral way of expressing the solution to these is that it allows us to kind of build in the information that we would have in an initial value problem. So for an initial value problem, we might have something. Well, let's look at this one. So let's go back to this example. We can make this an initial value problem by specifying the value of the function at some input. And so let's say y of 0 is equal to 2. Just coming up with this problem. So we could go through the steps like this. And when we get to the end, we simply say y of 0 is equal to 10. And when we plug 0 in here, we get 0 plus c, which is just c. We get c is equal to 10. And so our specific solution, so in this case, when we just had the differential equation, we were looking for a general solution. When we get that extra piece of information, that allows us to pin down a specific solution. So the specific solution in this case will be y of x is equal to x cubed plus c. Alternatively, we could have done this by saying y of x is equal to x0 up to x of 3s squared ds plus c. And we can build in this initial value condition by instead replacing c with y of 0 and using our initial x for our x0. Maybe I should have not done that by erasure. Let's go back. So that, yeah, the nice thing about this way of writing it is that it allows us to put our initial condition directly into the integral. So our initial x will be our x0. And of course, a lot of this is unnecessary because we know what the antiderivative of this is. Let's suppose that we did. And this will be our initial value. And we see that this all works out because if we take 0 and we plug it in for x here, we get the integral from 0 to 0 of something. And of course, this right here is just equal to 0. Right? So we're looking at the area under the curve where the area has no width, right? We're integrating from 0 to, we didn't go anywhere, we just stayed at 0. So the area is 0. So that's one of the nice things about this. Yeah, maybe this next example will be a little more clear. So this is one example. So in this one, we have the very famous expression. So the derivative of y is equal to this e to the minus x squared. And this will be an initial value problem. We will have the initial value of y is equal to 1. So y of 0 is equal to 1. So this is the same kind of setting. This is that easy case where the derivative of y is expressed completely in terms of x. So this right here is just totally a function of x. And so in order to get the solution, we get y of x is simply equal to, and now doing it in the definite integral form, the integral from 0 to x, e to the minus x squared, sorry, I should use a dummy variable, s squared es plus 1. And so this is our way of expressing the answer. Now, in this case, unlike the previous one, we knew what the antiderivative was immediately just by looking at it. In this case, we don't know what the antiderivative of e to the minus x squared is because there isn't one in terms of simple functions that we already know. So the antiderivative of this simply doesn't exist there's no easy way to write it down. In fact, the way that it's written down is simply this. So this is the antiderivative. This is just as an aside, this is a really important function in statistics. It sort of is the calculation of the probability of something happening when it's normally distributed. Anyway, yeah. So this is just an illustration of usefulness of this definite integral. Definite integral. So we started off with what we were calling the easy case, which is y prime equals f of x, which is the function of x. But what if we have y prime, and now this is a function of y. So this is a little more complicated. But if you recall, I think this is something that's talked about in Calc 2, maybe. So we have this theorem. It's known as the inverse function theorem. And what the inverse function theorem tells us is that if we have, we'll write this here, the derivative of y with respect to x, because, well, it'll be easy to show how to remember what the inverse function theorem is. If we have an expression for the derivative of y with respect to x, then we can immediately think of an implicit function of x with respect to y. So we can think that there's a function of x with respect to y that works as the inverse of the function at a particular point. So if we pick a particular x, we can find an inverse of y of x. So this would be a function x of y. And we can immediately tell what its derivative is. So the derivative of x with respect to y is equal just to 1 over, let me write it like this, 1 over the derivative of y with respect to x. And you see that there's a nice way of remembering this because it looks like we're just taking the reciprocal. On the one side, we are taking the reciprocal. We're taking the reciprocal of this f of y, because this will be 1 over of y. But on this side, it looks like we're taking a reciprocal of this derivative operator, which we always write, or we often write as a fraction, but we are constantly telling each other and our students that this is not actually a fraction. The reason that this is referred to as Leibniz notation is because, this notation was the notation that was used by Leibniz with his calculus. And he really did think of these things as fractions. So he thought of them as fractions of infinitely small things. And mathematicians and philosophers at that time in the, I guess, late 1600s, around late 1600s, early 1700s, they thought that this idea of talking about infinitely small but non-zero things was kind of a nonsensical idea. And maybe we were introducing paradoxes and unknown inconsistencies into our reasoning by dealing with fractions of infinitely small things. So mathematicians and philosophers of math people who were very interested in making sure that math was consistent and not saying things that were nonsense, insisted upon coming up with a framework for derivatives and integrals and everything so that we don't talk about these things in terms of fractions, infinitely small things. This is where the concept of the limit comes from, and you will, of course, remember from Calc 1 and Calc 2 that all of the concepts of calculus are framed in terms of the limit. So that was the idea that people came up with to get around thinking of fractions. But you can see from this example, very often it does work out to just simply treat them as fractions. So in the case of the inverse function theorem, the only thing that we have to make sure of is that this f of y isn't 0 because we don't have 0. So that was a free history lesson. You didn't pay for that. You got it for free. But it's, it's just a point to remind you that we really don't think of these things as fractions. Well, okay, I'm gonna leave that topic aside. It is possible to think about these things as fractions. A rigorous framework for doing. That's not a topic for this class. Okay, so let's do example number 3. And that was the example from yesterday. And that's the population growth. So this is the one where we're saying the real world situation that this represents is population growth where, each individual in the population, maybe think of it as bacteria. So each individual in the population has a certain probability every moment of splitting into 2 bacteria. So the rate at which the population is increasing is directly proportional to the number of bacteria. But of course, now we have this as a mathematical expression. We can think of this purely in terms of math. And that's nice because we know this sort of pure mathy thing, this rearranging symbols way of looking at it, which is we take this expression and we just say, well, there's an implicit function. Let's start off with saying, first of all, y of x equals 0 is a possible solution. But that's pretty clear. Is that clear? The derivative of 0 is just 0, and 0 times k is 0. And so that's definitely a solution. That allows us to get around the possible problem that might arise when I apply the inverse function theorem, which says that if we have this implicit inverse to y of x called x of y, then its derivative at the particular point where we decided to find the inverse is equal to 1 over ky. Right? So what am I going to say about this? Oh, yeah. We have a y in the denominator now, so we need to make sure y is not equal. So we have the derivative of this. This is now a function. This is the name of the function is x. It's written in terms of y. And we can just solve this just like before. So we've swapped the roles of x and y. Now we're treating x as the function and y as the variable. And so x of y is simply equal to, I'm just going to go back to the easy way of writing this. dy plus c. Right? And this is easy to get the antiderivative of, but I'm going to look at the notes anyway. Because it's really embarrassing when you're in front of a group of people and you mess up a problem. I'm going to try not to do that. We have that the antiderivative is this. And really, I'm just going to write it. Let's introduce another constant here, general constant d. Okay. Now, let's just kind of drop this x of y. We're just going to say x is equal to this because we're gonna go back and forth between treating x as the variable and y as the function. We're going to then treat x as the function and y as the variable. And now we have x in terms of y. We'll solve for y, and then we'll get y in terms of x again. So what we get is y is equal to, actually the absolute value of y is equal to e to the kx minus, because we multiply the k over, then we subtract the kd, right? Maybe I should go through the steps. Let's go through the steps. There's no harm in doing that. Multiply both sides by k. We get this. Subtract this over, and we'll make everything the exponent of an e. So this is e to the natural log absolute value of y equal e to the equal to e to the kx minus kd. Okay, so this gives us the absolute value of y is equal to. This is Calc 4. I'm sure you're used to going through all these details, but we got to do something today. Okay, so that's what we get. Now we can, let's see, what can we do? Well, first of all, we'll drop the absolute value because we know that e to any power is always a positive number. So we don't need the absolute value there. We'll just say y is equal to e to the kx minus kd. And we'll rewrite this e to the kx divided by e to the kd. Let's write it like this. Times 1 over e. Okay. Every time I write something, I feel like I've got a better idea. Let's do it like this. Okay. Now, this k was a constant, and this capital D, they're both constants. The D, in fact, is an arbitrary constant. And so we'll just take this whole expression because everything here is a constant. This is just going to be some constant. And so we'll write this as D times kx. And that is our general solution. So you remember from yesterday that, let me put it all together, y of x. Put a box around the final answer. So this is, you remember from yesterday that I was saying that we have this as the general solution to the, just as a reminder, scroll off the screen. Y prime is equal to ky. So have this connection between the two. This is the solution of, this is the general solution of this ordinary differential equation. And we talked about the fact that we didn't have a proof for that yet. Well, now we do. So if we just apply the stuff that we know from Calc 1 and 2, we get an answer. All right, we've got about 25 minutes left, so we can continue here. So the book has another example, and this is kind of an interesting one. Example. So let's find the general solution to this. This is something that we know how to do now. We'll note, first of all, that y equals 0 is a solution. Oh, let me go back to this problem for just a second. We did note also at the beginning here that y equals 0 is also a solution to the population growth, ODE. And down here in the general solution, we don't make any mention of it, right? Well, we can kind of fold it into this general form of the solution by just noting that C here could possibly be 0. So if we allow for the possibility that C is equal to 0, then that includes the solution that y is equal as well. Okay. So here we'll do the same thing. We'll say that y equals 0 is definitely a solution. And that allows us to set that case aside and assume that y is not equal to 0, which will allow us to say that dx dy is equal to 1 over y squared. In other words, y to the minus 2. And this we can integrate as well, or we can get the antiderivative of. So we can say that x is equal to, what do we end up with? Minus y to the minus 1 plus c. And maybe a nice way to write this, negative 1 over y plus c. Again, we end up with something that it's relatively easy to solve for y in terms of x. And so we'll go ahead and do that. We get x minus c is equal to minus 1 over y, or c minus x is equal to 1 over y, or y is equal to 1 over c minus x. And that gives us our general solution. Now, our general solution has a singularity at x equals c. So it has the value of our solution goes to positive or negative infinity as we get close to x equals c, and so we really only have this thing defined for a region outside of that. Anyway, that's a technicality that we can kind of gloss over. The next example, suppose a car drives at e to the t over 2 meters per second, where t is time in seconds. How far did the car get in 2 seconds? How far in 10 seconds? You know what? I'm going to skip this because I hate word problems. And it's the same kind of thing, right? It's really just, we can write this as an ODE. It's really just an integral in disguise. And so we know how to do that. We've seen something. So we'll skip that. Now, there's lots of exercises at the end of the chapter. Skip over those. And go to the next section, which is not what I was expecting. The schedule does say that we're talking about existence and uniqueness. Okay. So that is next section of the book. Wrong. Well, I guess they use that as a segue for the concept of existence and unique. I'm going to have to clear this. I've gotten to the bottom apparently. Okay. So, yeah, let's go ahead and talk about this. So the next subject that they talk about in the book is slope fields. And I guess in the notes and in the schedule, they refer to this as direction fields. So what's the idea here? This is a way of qualitatively examining first order ODE. And the only thing I mean by that is that this is a way of understanding the behavior of the solution without actually getting the solution itself. So, and in fact, visually understanding. So what do we have here? I think actually you see a little bit of this at Calc 3, so you probably are already familiar with this. But what we have is for a first order ODE, we have this y prime is equal to f of xy. So we really get some number for every input x and y. We get the derivative of the function at every x and y. Now this is kind of nice because what we are putting as the input is points in the two-dimensional plane. We have an x coordinate and a y coordinate. So we can really just take the good old coordinate axes, and we can say, so at some particular x, some particular y, then at this point right here, we know what the slope of the function is. If the function does in fact, if the solution does in fact go to the point x, y, then we know what its derivative must be, right? So if the function goes through this point, we know what the tangent line looks like, right? If we have the derivative and we have a point that the function passes through, we have a point that the function passes through, and we have its derivative at that point, then we can compute its tangent line. So what we do with these slope fields is we say, let's suppose f of, let's say this is 3, 1, and we say f of 3, 1 is equal to 2. Then what we do at this point is we draw a little arrow, little tiny arrow. Looks like this. I can't see what it looks like for you. I can't see what it looks like on the tablet, but kind of a small arrow. Let's try that. The slope of 2 kind of looks like maybe this direction, right? It's steeper than 1, not as steep as 3. I don't know. This is all just for illustration. So we kind of do this for evenly spaced points throughout our coordinate plane, throughout x and y. So maybe it looks something like this. And then if we go up, it looks like this. And then here, maybe it kind of looks like this. Here, it kind of looks like this. Let's extend it a little further. Okay. So now, if we say, for example, that we have not only our differential equation, but we have an initial condition. And our initial condition will be, let's say, y of 3 is equal to 1. So our initial condition says at the value x equals 3, the value of our function is 1. And so we know that, write it like this, our specific solution passes through the point 3, 1. So it does in fact go through this point right here. Oops. Go back. There we go. Okay, so it does go through that point. And what we can do now with the slope field is we can kind of guess what the rest of the function looks like. So as it passes through this point, it kind of goes in this direction, right? Because we know what the tangent line is. As it passes to that point, the tangent line has that same slope as the slope field there. And as we go up, this kind of has the slope like this here, and it kind of goes like this, right? And so maybe we kind of guess that our function, our solution, kind of looks like this. So we have a kind of feeling for what this function looks like. So that's the usefulness of slope fields. The book actually has a couple of good examples. Well, you can look at that in the book. Um, the same sort of thing. Let's say we had, instead of this initial condition, we had the initial condition that, okay, let's say right here, that y3. So that level right there. And it looks like on this level, all of the slopes are 0, right? It looks like our function will just be going straight across. So let's say instead of this initial condition, we had the initial condition y of 3 is 3. Well, in this case, we're guessing that our function kind of looks like this, right? Kind of, I get other colors. Oh, yes, indeed. Okay. Right. We might get something like that. So the slope field is giving us a kind of idea without actually telling what the solution is. It's giving us a kind of a feeling for the way the solution will behave. Solutions, it seems, kind of have the behavior that they kind of zoom in on this line right here. Now we get kind of a feeling from this that if our slope field is nicely behaved, if it looks sort of reasonable, then and we have an initial condition, then we can say exactly what the solution is. We just follow the slope field. That's all it is. So that introduces us to one of the fundamental questions in ODE. So that question is I'll write it like this, the existence, and again, go easy on me. I think I might have dyslexia or something like that. The existence, uniqueness theorem. I misspell things all the time. So the existence uniqueness theorem question. I want to say this is the question. We will have a theorem related to this in a moment, but right now it's just a question. So first, given a initial value problem, is there solution? Does a solution even exist? That's of course an important question. If we're trying to find the solution, we're working really hard to try to get what the solution is. Turns out that it doesn't even exist. So that's an important question. The second question is, given a solution exists, is it unique? And of course, this is the unique. So given one particular solution, do we know that that's the only solution? Or is there another solution that would work as well for this? And the feeling you kind of get from our discussion on the slope field is maybe, yeah, if the slope field is at least nice enough, we know a solution exists because we just start at a particular point and we just follow the slope field. Whatever the initial condition, wherever the initial condition tells us to start, we just follow the field and it's the solution. And it looks like, given that slope field, there's only one direction that we can go, so it should be unique. Now, these questions are posed in general. They're not just for first order ODEs. So the nice thing about the first order ODE was that we could draw a slope field because our ODE. We'll go back to it again. So all that we have is the first derivative of the function, and that first derivative can be written in with no reference to the second order derivative or the third order derivative or the second order times the first order or the second order times y or anything like that, right? We were writing it totally in terms of x and y. So we just plug in an x and y and the derivative, the first derivative. That's not true in general for ODEs. That's what makes this a really nice situation. So we ask these questions in general, but it does really seem like for first order ODEs, it's true. And again, they've got some nice examples in the book, but it's going to be too hard for me to draw. But we do get down to this theorem. And it doesn't look like they give a proof of this. It would be a little bit difficult for the second day of undergraduate differential equations class to go straight into proving this very important theorem, but we'll just state it. And you already have a feeling for why it should be true. So this is called Picard's theorem, named after the French mathematician Émile Picard, not Jean-Luc Picard, captain of the Starship Enterprise, on existence and uniqueness. Okay. And basically what it says is that if our slope field is sufficiently nice, if our f of x, y, the function that we have for our first derivative is sufficiently nice. Let's write it down. Put it right. God, what? There we go. Specifically, what does it say? If fxy is sufficiently nice, and by sufficiently nice we mean is continuous, right? That was the assumption that we were making when we were going from one of these little arrows to the next. Is that in between the arrows change in the not crazy way, right? The same way. If f of x and y is continuous as a function of two variables, and the partial of f with respect to y exists. So it's continuous, and we can take its derivative with respect to y. And that derivative is also continuous. So this is enough to say in fact, we only need it locally. We only need it right around that point, x0, y0. Then a solution to y prime equals f y with an initial condition, y of x0 equals y0. So that's what this takes care of right here. So as long as our slope field is sufficiently nice around our initial point, then the solution to this exists. I'll rewrite it like this. I think this is a little nicer way of stating it. It exists and is unique, at least near x0, y0. So as long as we stay close to that initial point, we can be sure that there's a solution and it exists. And that is that's exactly what the conclusion that we came to from playing around with the slope field. Okay, we got 5 minutes. What's left? Oh, so this condition right here, we call this, it exists in unique, it exists and is unique locally. So we can guarantee that it exists and it's unique, at least right there. Now, that's because we're only insisting on these nice properties. It's continuous, its partial is continuous. We insist on it having these nice properties near a particular point. If it has these properties everywhere, then we would say that the solution exists and is unique globally. So this is one of these fundamental distinctions in mathematics between what's true locally and what's true globally. Okay. So 4 minutes left. I guess we have time for let's see. It's a good example. Yeah, sure. Okay, so let's say y prime is equal to y squared. Y of 0 is equal to, they say a, let's just say 1. So we have its derivative. In fact, we know how to solve this thing. We say dx dy is equal to 1 over y squared. We know that y is not, let's write it like this. Y is not the 0 function, right? We know y is not identically 0 because at least one point, y is not 0. So we can go ahead and write this dx dy over equals 1 over y squared. Let's see. Okay, so we've done this before. Y to the minus 2. X is equal to minus y to the minus 1 plus c. And so we get y is equal to 1 over, work out to be 1 over c minus x. C minus x. Okay, and we can figure out what c is because we know that at x equals 0, so 1 over c, we get y is equal to 1. So we get c is equal to 1. Make a little room. And so we get y is equal to 1 over 1 minus x. So we already have a solution to it, and we already know the solution is unique. At least around, at least as long as we're not right at x equals 1, right? Because there we assume that we have no solution because it kind of blows up to infinity or negative infinity depending on the direction. Now we could have used this theorem instead and said that a solution exists and is unique without actually getting the solution. So we'll go back and take a look at f of x, y. This is just y squared. So is this continuous? Yes. It's just a polynomial in y, and we know that all polynomials are continuous. The f d y. So the partial derivative of f with respect to y is 2y. It's an easy partial derivative to take. We treat all of the x's as constants. They're not there at all. And we take the derivative, so that gives us 2y. And this is continuous. And so without even getting the solution to this differential equation, we have that a solution exists and is unique. So it exists and is unique near, well, we can just say near x equal to 0. And so that works out. Okay. Oh, it's 11:20. I should probably stop now. I'll stop talking about math. I'll ask you if you have any questions. So do you have any questions? I'll stick around for a minute in case you do. But other than that, we'll call it a day. So thank you. See you hopefully tomorrow. You have a question? No? Okay, goodbye.